In this video we have three problems and we're to find the location of any relative extrema. Now this refers to either a maximum, a relative maximum, or a relative minimum. You want to pause the video and try this? Go ahead, and then I'll be right back. Now these types of problems, especially these three that I have here, you can actually work these without the calculus. You can graph and use the menus from the graphing calculator to come up with the answer to these problems. But we want to use the calculus. Number one is a parabola. So let's go ahead and just explain this. If a parabola opens down this way, you got a vertex right here, say at HK. That's your relative maximum. In this case, it's an absolute because that's the highest point. Or if you have a parabola that opens up at the vertex, right there, you have a relative minimum. And again, it's an absolute minimum because that's the only one. Now if you have a polynomial, say right here, goes up here and it comes down, and then it goes down and it goes up, continues up, and then it reaches the high point, it comes down. So here we have two relative extrema where it peaks, like in the first one at x1, y1, you have one relative maximum, reaches a high point and then it turns. And then x2, y2, you have a minimum. It goes to a low point and then it rises, it goes up, and then at x3, y3, it reaches another high point, another relative maximum. So that would be your absolute one, because the curve goes down on the left and down on the right. That's the highest point, and the x2, y2 would be an absolute minimum. Now the procedure for finding these on a particular curve, in this case we're dealing with a polynomial graph function, is to find the critical numbers. In this case, I tell you that the critical numbers are x1, x2, x3. So first of all, what is a critical number? A critical number is a number, and it has to be in the domain of the function. In this case, we're talking about y equal f of x, where the derivative is 0 or undefined. Remember, it has to be on the graph. It has to be in the domain, so it has to be on the graph. So can't happen at a point of discontinuity. And I want to point out here that f prime, if I start with the first one here, is positive here. And then on the the right, the derivative, or the slope if you want, is negative. So if you look at this, for the first one, right here, at x1, y1, we have a relative maximum. So what we do is find where the critical number is. And that's the first component there. And if to the left of that value the derivative is positive and to the right is negative, then that is a relative maximum. Now at x2, let's say this value right there is x2. To the left the graph is falling, so when the graph is decreasing, the derivative is negative. So to the left it's negative, and to the right it's positive. When the curve is falling and then rising, then you have a relative minimum. Talking about the derivative or the slope. So it's rising and falling. On the next one, it's derivative negative to the left of x2, and it's positive. So it's falling, and then it's rising. It reaches a minimum there. And on the x3, y3, to the left here, the derivative is positive, and it gets that high point. At the high point, of course, that's where you have your tangent line. Or over here, you have a tangent line on that one. Or over here, it's a tangent line. Positive derivative to the left at this high point here, and then negative over here. And that's how you find where you have the relative extrema. So let's go to the first one then, and just find the derivative. Now this is a parabola. It's like I said, in this one all you got to do is find the vertex, and you can do that without any derivatives, but we're using derivatives here. Let's take the derivative of this. This is going to be minus 4x. Derivative of 4x is a plus 4. And the derivative of a constant 3 is 0. So again, if you're asked to find the location of any relative extrema, that could be a maximum or minimum, find the critical numbers of the function. You do that by simply taking the derivative, and then find the values where the derivative is either 0 or undefined. Now here we have polynomial. So a polynomial is going to be defined everywhere. So now this one is going to be 0. Set this equal to 0 and to solve it, you can see that x equal to 1 is a critical number. So all you do is plot that number on a number line. That's 1. And all we have to do now is check the derivative here to the right of 1. Infinity is over here. Negative infinity is over here. So pick a number larger than 1, say 2, and put it in here. And this is negative. Negative to the right. Pick a number less than 1, say 0, and it comes out positive. So then we examine this. Remember, we're talking about the derivatives. This says to the right, to the left of 1, the derivative is positive. So that means the graph goes up, reaches that high point, and then to the right is negative, comes down. So this tells me then that I have a relative maximum at the point 1, and then you go back to the function, put a 1 where the x is, as a minus 2, a plus 4, and a 3. That's minus 2 and 4 is 2, and 3 is 5. So the location, in this case, of the relative maximum is at 1, 5. That's the location. So they tell you, well, what is, or they ask you, what is the maximum in that particular interval? Well, it's 5. And it occurs at what value of x? Well, it's 1. So the actual location, we just say 1 and 5, the 0.15. Okay, next one. Now this was not a parabola. So to work these out, the first thing we have to do, compute the derivative. Term by term, it's a polynomial, so it's pretty straightforward. This is going to be 3x squared minus 12x. Derivative of a constant is 0. So that's what we get. Now we want to find out the critical numbers again are numbers in the domain of the function for which the derivative is either 0 or undefined. So here we can just factor out a 3x here. So we get 3x times x minus 4. So we want to know when is this 0. And that's pretty straightforward. You can see that 3x is 0 at 0. X minus 4 is 0 at 4. So the critical numbers for this particular function are going to be 0 and 4. So any relative extrema that we have, again, a relative extrema refers either to a maximum or a minimum. Anyway, those are going to occur at 0 and 4, if it has any. Now, it is possible that you could have a critical number that leads to no relative extrema. You have to check it using the first, what we call the first derivative test. So we plot the critical numbers on this number line, and then you just determine the sign to the right and to the left of each value. So pick a number larger than 4, say 5, put it in there for x. You can see this is going to be positive here. Pick a number between 0 and 4, say 2. This will be negative. To the left of 0, pick a number less than 0. Anything will do. Negative 1, put a negative 1 there, negative 1 there. And this comes out to positive. So again, the positive tells you that the curve is rising. Positive derivative means the curve is increasing. Negative means it's decreasing. So this one, to the left of 0 then, positive, so it's rising like that. And then you get to 0, and it comes down. So you can see, that's the maximum. At that 4, negative to the left, means the graph is falling. And then it reaches that point there where it has the critical number. And remember, the critical number leads also, that's where you have the tangent line. And then positive goes like that. So now we know that we have a relative maximum at 0. Just to get the y value, just plug it into the original function, not the derivative, okay? This goes back to the original function. So put a 0 where the x is 0, 0, and you get 15. So relative maximum at 0 and 15. This is from what we call the first derivative test. And the next one then be relative minimum at the point where x is 4. That's the critical number, so we put a 4 there. And then to get the y value of that minimum, go back to the original function here, plug in 4 where the x is, and that should give you a negative 17. So again, the relative maximum occurs at the point 0, 15. The relative minimum occurs at the point 4 and negative 17. A rational expression here, take the derivative. Here we'll have to use the quotient rule, and that simply tells me that I have to take I square the denominator, and then in the numerator is the denominator times the derivative of the numerator. So you just take the derivative there. This would be 2x minus 2. And then it's a minus the numerator. So that's x squared minus 2x plus 1 times the derivative of the denominator. Derivative of x plus 1 is 1. So you got this right here. So then we'll go ahead and simplify. So multiply x plus 1 and 2x minus 2. And that'll give us 2x squared minus 2. And then we have minus x minus in parentheses x squared minus 2x plus 1. And if you simplify that, combine and so forth, multiply out and combine, this is going to give us x squared plus 2x minus 3. And this should be a square here. X plus 1 squared here. So again, it's just 2x squared here and then a minus x squared. We got the x squared here. They get a minus minus, we get the plus 2x, and then the minus 1 and the minus 2 is minus 3. So we're going to end up with that. And then we can factor this out. The numerator will factor into x plus 3 and x minus 1. So when is this 0? That we need to find the critical numbers. So the critical numbers come from numbers again that make the derivative 0, or they could come from numbers that it's undefined. So what are the numbers where it's 0? Well, the critical numbers, of course, are going to be negative 3 and 1. Remember, a derivative can only be 0 if it's a rational expression like this one, if the numerator is 0. So the numerator is 0 at negative 3 and 1. Now the derivative is undefined at negative 1, because if you put a negative 1 where the x is in the denominator, you get 0. Division by 0 is undefined. But remember, the critical number has to be in the domain of the original function. So over here, if you look at the x plus 1, negative 1 is not in the domain because the function is undefined at negative 1. So again, keep in mind, critical numbers are numbers that make the derivative 0, or come from numbers that generate a 0 for the derivative, or numbers in the domain of the function where the derivative is undefined. So again, it is undefined. Derivative is undefined at negative 1, but negative 1 is not in the domain of the original function. So we can only use the negative 3 and the 1. So with that in mind then, we plot the negative 3 and the 1. Infinity over here, negative infinity over here. So pick a number larger. Let's go back, look at the numerator here. The denominator is always positive, so we just ignore that. To the right of 1, we pick, say, 2. The derivative is positive, so it's positive in here. Between negative 3 and 1, say pick a 0. Comes out to a negative. Pick a number less than negative 3, say negative 4. Negative 4 and 3, negative 1, and negative 4 and a minus 1, negative 5. That's a positive, so both positive, so, or negative times a negative rather is positive. So it's positive in here. So again, to the left of negative 3, the derivative is positive, so the curve is rising, and then negative, so it's coming down. To the left of 1, I have a negative, so the graph is coming this way, and then it turns at 1, it goes to, after 1, it goes to positive, so it's rising. So here we go then. We have a relative maximum at, look at the graph, negative 3, and then plug in negative 3 into the original function, that's 1 over here, and compute that out. You should get a negative 8. That's just arithmetic. And then we have a relative minimum at 1. And you go back and plug that in. Notice 1 squared is 1, and then 1 times the minus 2 is minus 2. So we're 1 minus 2, and then 1 gives me 0. Denominator will be 2, so this is 0 here. And that's the solution to this one. And a relative minimum at the point 1, 0. Now if they ask you what is the maximum, the actual maximum, well, for the first one, it's negative 8. What's the actual minimum? You look at the second point, 1, 0, it's 0. But in this exercise, we're finding the location. So we're given the point where the maximum or the minimum occurs. Thanks for watching. We'll see you next time.